Hi, and welcome to part 2 of a Calculus 1 video on the definite integral. What's important to note is that in our first video for the definite integral, we made a connection between the notation, which I have right here in the center of my screen here, this notation, of the antiderivative from 0 to 10 of the function. We made the connection between that notation, the area of those rectangles, and that graph that we get. So what we were really connecting was the fact that we are still using rectangles to approximate the area under the curve. And so what we can actually say is the antiderivative from a to b of some function. So I'm going to integrate f of x with respect to x, so f of x dx. This is the area under the curve f of x from a to b. So we have this notation now linked to area. And right now we're doing that by approximating with rectangles. So that's where we went with this problem. So if you haven't checked out that part 1 video yet on the definite integral, I really suggest that you do. Let's just take a look at one where all we're given is data. So we've got this question right here. A table of values of an increasing function f is shown. Use the table to find the lower and upper estimates for the antiderivative from 10 to 30 f of x dx. So I am looking for the area under the curve from 10 to 30 in terms of x, and that's exactly, if you'll notice, what my table goes from and to, so that's a good sign. And I want estimates for the lower and upper, so which means I'm going to use left and right approximations. So when I look at this table, I can see that delta x is a constant 4. I am always increasing by 4. So delta x is 4. You want to use as much data as you have, because the whole reason for calculating the data is so that you can use it to get the best approximate value for whatever you're trying to do. So since we have that data, we're going to use it. So delta x is 4, and remember delta x did have a formula. It was your end minus your start, or b minus a, all over n, which was the number of rectangles that we were going to put in. So I could go backwards and figure out how many rectangles am I going to put in, because my delta x in this case is 4, my b value, or my end, is 30, my a is 10, and I can solve for n. So that would be 20 over n. So n must be 5. So I'm going to put in 5 approximating rectangles. And if we think about what this is going to look like, if I'm starting at x equals 10, let's say x equals 10 is approximately right here, and my delta x is 4, that means the width of that first rectangle is going to be 4. So if I carry up the left edge, or the left side of that, and figure out where my function's value is, I'm using the left endpoint to determine that rectangle's height. So if I'm using left endpoints, I'm going to use the y value or function value for x equals 10. Then if I think about the next rectangle that would go from 14 to 18, I'm going to use wherever my function value is at 14, and then I'm going to go over. So if I think about it graphically, sometimes that helps. Okay, so my left endpoints, so I'm going to say area left. We're going to calculate it this way. So there's my first rectangle. Here would be my second, my third, my fourth, and my fifth. One other thing that you might want to do is, since you're calculating left, I was using L to denote left, you may want to put it on the left side of your data box. So I may want to say it like this: L, 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 L. All right, so the area is going to be the width of each rectangle, which delta x is 4, times all of these subsequent heights. So negative 12 plus negative 6 plus negative 2 plus 1 plus 3. And that should give me 4 times negative 16, or an area of negative 64. Now, I'm not going to necessarily say right now whether that's a lower estimate or upper estimate. Let's go ahead and find the other one, and we can determine that. So the area of the right, again, all of my rectangles are 4 wide, so I will say 4. And now, where are my y values? Well, if I think about my first rectangle going from x equals 10 to x equals 14, the right edge or the right side of it would be at that x equals 14. So that y value would be -6. So my function value for the right endpoint would be -6. So that would be my first height of my first rectangle. So that's the first, here's the second, here's the third, here's the fourth, and here's the fifth. Because again, if you think about that final rectangle going from x equals 26 to x equals 30, the right edge, you would carry it up or down. Just figure out where it crosses your function. That's what's going to determine the height, wherever it is, of your rectangle. Okay, so I am going to add these up now. -6 plus -2 plus 1 plus 3 plus 8. So that's 4 times 4, or 16. And you should be able to take a look at these answers, even if you didn't know from before, and tell me which one is the lower estimate and which one is the upper estimate. My negative value is my lower estimate, and my 16 is my higher value for area, right? Comparing -64 to 16. So that's my upper estimate. I could also see this because if you take a look at your y values, as you're looking at these function values, they are getting larger every time. In other words, I have an increasing function, which it also told me in the problem. So if you have an increasing function, I can go ahead and just draw a random increasing function. There's an increasing function. And you think about the left endpoint determining the height of that rectangle, it'll always be lower than the right estimate because my right estimate would have been up here, and that would be the over estimate. So if it's an increasing function and you're looking at those left endpoints, they'll always be lower than your right endpoints because your left point will be lower than your right point. And so that will be the case too. So I could have known that that was my lower estimate and my upper estimate from a few different ways. Hopefully this helps. I really hope you're connecting the idea of the rectangles. We're using a finite number right now to approximate an area under a curve, and this is the notation, right, that we're starting to work with right now. They never said find the area under that curve from 10 to 30, but that is what that notation is asking me to do. I hope you found this video helpful. Thanks for watching.